Gravity is arguably the first scientific concept we learn about as humans. Although we often only pay attention to it during the heart-stopping moment of a fall, or in the beauty of the autumn leaves as they float to the ground, gravity affects us every second of our lives. But how do we measure it? How do we quantify it so that we may better understand it? The purpose of this lab was to measure gravity and quantify our results. While we generally use 9.80 meters per second as our gravitational constant, the exact value changes depending on location due to the varying density of the Earth. Our group decided to conduct a very simple experiment, using a ping pong ball, a 1 meter long ruler, the stopwatch function of an iPhone, and the slow motion camera function of a second iPhone. The first iPhone was propped up next to the ruler and the stopwatch was started. The bottom of the ping pong ball was aligned with the 0 mark on the ruler and then dropped, allowed to fall 1 meter and then bounce off the table. This process was filmed using the slow motion function of the second iPhone, and we ensured that the stopwatch was visible on the video. We were able to analyze the footage and see the precise moment in which the ping pong ball left the hand of the group member holding it, as well as the precise moment it made contact with the table after its fall. The stopwatch in the footage was used to measure the length of time it took for the ping pong ball to fall to the nearest 100th of a second. This process was conducted a total of 4 times before we calculated the average time the ping pong ball took to fall to be 0.43 seconds. The first thing we needed to do to work out the value of gravity was calculate the velocity of the ping pong ball. We did this using the equation speed equals distance over time, where distance is measured in meters and time is measured in seconds. The value of gravity was then calculated using the equation g equals 2 times the average velocity divided by time squared, which gave us the value of 10.82 meters per second. This value is significantly higher than the gravitational constant of 9.80 meters per second, so we were particularly interested to see what the value of the calculations of uncertainty would tell us. To work out the uncertainties, we took half of the smallest unit of measure of each of the variables. Because we used the slow motion camera to capture the experiment, the frame rate played an important part in the variable of time for the calculations. The model of iPhone used to capture the experiment had a frame rate of 120 frames per second for its slow motion function. The uncertainty for time was calculated using the formula time over frame rate divided by 2, which gives us this value. Next, we used these values to calculate the upper and lower limits of our gravity measurement. The upper limit was calculated using the formula 2 times the maximum displacement over the minimum time squared, which gave us 11.03 meters per second. The lower limit was calculated using the formula 2 times the minimum displacement over the maximum time squared, which gave us 10.60 meters per second. Even after completing our uncertainty calculations, our value for gravity did not equal the gravitational constant of 9.80 meters per second, which suggests that there were significant errors in our experiment. This is likely due to the lack of precision when measuring the height from which the ping pong ball was dropped. Another potential source of error is one of the time measurements used to calculate the average was significantly larger than the data points, which indicates a possible error in our slow motion analysis. In a future experiment, we would pay close attention to the height of the fall, as well as do a more thorough analysis of the slow motion footage.